Our next speaker is Tabor MacCallum. Tabor is the current chairman of the Commercial Spaceflight Federation and co-founder and chief technology officer of Space Perspective, and he's going to be speaking to us about Space Perspective. James, is Tabor here?
I'm going to talk about Space Perspective, which is a space tourism company that we've been starting up this year. What we're wanting to do is give access to an edge of space experience, seeing the world from the edge of space. But I want to sort of put this in the context of pathway to how we got here. And that pathway is really on the way to Mars. So I started my career actually on this ship for about 2 years. And part of what was fascinating about being on a ship for 2 years is that's sort of the time it takes to get to Mars. And having a sense of how long that was and sailing much of the way around the world in that time period, I happened to be on the crew that was brought from that ship to do a project called Biosphere 2. And what's interesting about that, so this is the mid 80s now, and Buckminster Fuller had dared the Bass family essentially to go build a biosphere. And the biosphere is, essentially the fundamental unit of life. If we're going to take life into the solar system, if we're going to live on Mars, if we're going to be a multiplanetary species, we're going to be taking our biosphere with us in one way or another. So the idea of the Biosphere 2 project was to test the idea that you could build an artificial biosphere and one day build biospheres on Mars, and that they would be self-sustaining. In the process of doing that, we built this little test chamber we called the test module to test out life support systems, water recycling, air recycling systems and actually the very first test data that was published from these early experiments was at the Case for Mars conferences. And so there was, Carol Stoker and Penelope Boston and Chris McKay were all there. And, I sort of nervously presented all of the data that we gathered about trace contaminants and a methane buildup issue that we had and some other problems with carbon dioxide, and just sort of laid out where we were in the pathway of building systems that could go to Mars. Remember, this is the mid 80s. So, NASA had never failed to execute on a mission that had been given. So the space shuttle was flying, and we were on our way to Mars, and so Biosphere 2 was sort of in that line. Also, a commercial space operation. Right now, that same test module is being transformed by Staats, who is actually going to present on this later on. It's called SAM Bio 2, the analog for Mars at Biosphere 2. And they're turning this system into an analog system for Mars. And Paragon, one of our companies, is doing parts of the life support system inside of the module. So it's sort of like coming full circle. It's great. It's going to have a big Mars yard. And you'll hear all about this later, but I'm very excited to see some of this hardware. So a bit like the Phoenix lander being reused, we're seeing this test module being reused for exploring Mars technologies. Space Biospheres Ventures was a commercial company developing life support technologies for use in exploring the solar system, and also helping us understand sort of how our Earth works with an agriculture and a habitat and desert and the like. And I was on the design team and a crew member for 2 years and 20 minutes inside. And this is me going in, and that's the Biosphere. And I think the basic result of the Biosphere 2 experiment was that humans have a really hard time in isolation and confinement. And there's a great book that Jane Pointer wrote about how crazy we all went, and that there were no fundamental issues with making an artificial biosphere, that Bucky Fuller's challenge to us was met. And while we had lots of issues, all of those issues could really be tracked back to the design of this particular biosphere, not sort of the act of closing up a small biosphere. From Biosphere 2, a gang of us got together and started something called Paragon Space Development Corporation, which is going great guns now, and has done parts of and hardware for virtually all human flight systems, either design or hardware. There's the thermal control system on Dream Chaser, a lot of work on Orion, humidity and systems on the Boeing vehicle. So that brought together a collection of technologies for going to Mars. And one of the first things that we actually did at Paragon was take some of the principles we learned in Biosphere 2 about how to make these closed ecosystems and challenge ourselves with would those work in a microgravity environment? Because that was one of the things that obviously we couldn't test in Biosphere 2. So we made a teeny tiny biosphere and actually flew it on the shuttle and to Mir. We bred the first animals through a complete life cycle in space, and was also the first commercial payload on ISS. So we're finding that living systems are actually quite pliable and can be rearranged and put together sort of the way we do DNA now into living systems that can support life and animals. Another fun project on this path to space perspective was something called Inspiration Mars, where Dennis Tito put in a bunch of resources to look at, can we take all existing technologies and do a Mars flyby? And we had a lot of support from the Mars Society, a lot of great work from NASA, and we worked out a bunch of different concepts. And I think really showed in a big report that a Mars flyby mission is possible. And I think as one of the big dragons of going to Mars is, can you get there? As Bob Zubrin said, this gets one of those dragons off the map. And so we thought it was really important to figure out how to do just a flyby mission. Just let's conquer that getting there part technically. And maybe the most important part of that work that we did was to actually build real hardware. We put together a system of hardware that had all the life support components that would be needed for that kind of a 500-day mission: CO2 recycling, oxygen generation, water recycling. We actually did a lot of work with solid oxide electrolysis. So this was after MIP, but before Oxy. And put it through its paces and really created an engineering baseline for the transit to Mars from Earth. And solid oxide electrolysis is on its way to Mars now. The water recycling component of that, which was based on really transpiring, much the way leaves transpire water to purify water, to get to about 98, 99% water recycling. And that system is on its way to the International Space Station probably later this year. So leading now to getting closer to balloons, there has long been a science fiction idea of taking people in a spacesuit up to the edge of space. This is 1934. Alan Eustace, as we were talking about this whole idea of taking people to the edge of space on a balloon, said, let's do a project, and I want to go to the edge of space. So we took him to essentially 136,000 feet and dropped him at Mach 1.22 on the way back, and did a lot of work in aerodynamic stabilization and the like. But what was relevant for Mars was the suit we built. This was the first actually utilized spacesuit, new design of a spacesuit built in 40 years. The American suit is still based on the Apollo suit, and of course the suit is based on the Russian suit, and that hasn't changed either. And we wanted this to be a super rugged suit. We only had one suit, and it had to go through all the testing. And this turned out to be an interesting analog for a suit that you would use to work on Mars. We had double seals. We had really made it strong in a sense of robust utilization. This is during jumping out of airplanes to test its low velocity aerodynamic stability, controllability and the like, and you see rollerblades on the front of a spacesuit because we had to roll him out of the aircraft. So this is probably the only time you're going to see rollerblades on the front of a spacesuit. In these early tests, we would have skydivers with him to get him down to Earth safely if he couldn't actuate something. But then what became really interesting in terms of the Mars analog was the landings. They were not very graceful. As you can see, Alan did lots of tumbles and turns in the dirt, and we would dust the suit off and fix the broken bits, and we'd be out flying the next day. We did it over and over and over again with one suit, very analogous to the kinds of treatment that one would imagine a worker on Mars the kind of abuse that suit would get. Here's another series of graceful landings by Alan. For a number of reasons, we could never get a running or a spun landing. He always did these topples over in the fine sands of southern New Mexico. So after all that, this is the third launch. We did flights in 3 weeks, so pretty much on a 1-week cadence of flights, which is the closest to that in human flight is 6 months between flights. So we also got this to a very high operational cadence, which is sort of the key. Reuse and high cadence, as I'm sure we've all heard through this conference, is a key to what we're trying to do going to Mars. And this is the very tip of the top of the balloon is inflated there, but that's a 17 million cubic foot balloon that will become perfectly round above that little speck of Alan at the bottom to give you a sense of scale of these balloons. Quickly, this is right before him releasing to supersonically skydive back. This is that initial sequence with the stabilization system deploying for the spacesuit, and then him coming down for another of these ingraceful landings. And that's the team. And it's also important to note how small a team can do these kinds of things. This is the primary and 2 backup medical teams. This is the launch team, all the engineers. This is the chase crews. This is what it took to pull that off. And it's a pretty small number of people, which is in large measure why we're able to do the cool things you're doing in commercial space now, because we can do a lot with a dedicated small crew of folks. We learned a lot about the stratosphere in those flights, which led to an unmanned platform at Worldview, which we started after Paragon. That on the right is about 400 feet or so. Those 2 bulges in the middle are ballast tanks, and this operates at about Martian atmospheric pressure. And sort of it can get up to 90-odd thousand feet in the air, and is a really interesting example of altitude controlled balloons that could fly at Martian atmospheric pressure. So all of these sort of things take us along the road to back to space tourism. And so I think this is fundamentally on the road to what we want to do, because we need a strong base. I mean, we have the technology, right? So what I've just sort of gone through, and if you combine all this with all the other great work that's being done, and Blue Origin and SpaceX, the pieces are there. But I think somebody said earlier in the launch, is there a will and a way? And we have a way, but we really need to make space flight more accessible, create a foundation of work for space exploration, for science, make space flight simply easier to do and more commonplace. So this is the concept that we're working on. We're venture backed, and we are now really fully engaged in hiring. Now, the basic idea is to lift off from the land, go to 100,000 feet at a blazing 12 miles an hour. So it takes about 2 hours to get up there for 2 hours. enjoy the view, you know, do what you would like to do. Jeff Hoffman calls this the quintessential astronaut experience, the just sitting, looking out the window, slowly descend back down and splash down in the ocean. And that's done largely for scalability reasons. It's much harder to do a land landing repeatedly as an operation than it is to do a splashdown with this kind of a system. It's 8 passengers, 1 pilot. Of course, there's a bar and a lavatory. All real spaceships have a bar. And you sort of get an idea of the layout and size there. We're setting this up to be launchable from a variety of areas. We're now working with actually all 3 spaceports in Florida to launch from those spaceports. We're regulated just like Virgin Galactic or SpaceX as a commercial launch. Our operations center, first operations center, is here at where I'm talking to you from at Kennedy Center. We are in that building there at the central line of the shuttle landing facility for getting ready for launches. And we're going to have our first test flight, an unmanned, full-scale but unpressurized capsule Q1 next year to start going through some of the CONOPS and other issues. This is launching from Kennedy, and I'm going to make sure I leave some time here for questions. Florida is interesting for us in operations because the stratosphere goes east part of the year and west part of the year. So part of the year will splash Atlantic and part of the year will splash down in the Gulf, launching from Kennedy Space Center. So Florida actually turns out to be a quite elegant place for us to have initial operations, and you know, Kennedy quite iconic, and it's great to be working here. The folks here are just terrific. We also have a lot of very interesting science applications because we're doing route profiles of the atmosphere up into the stratosphere. We're able to do measurements of things like mixing rates by doing precise measurements of carbon dioxide, for example. So there's a lot of actually very interesting global change science that we're looking at as part of the program. And then we do a water recovery after splashing down, quite analogous to what Dragon and Crew Dragon do. And that essentially the presentation on what we're doing at Space Perspective. I do think it's really, really important for us to make space flight accessible, and that people see that we live in a small planet with a thin atmosphere, and sort of get what, you know, Alana earlier today called, you know, the risks that we have being, you know, stuck on this one planet. And I think the more people that have that experience and give that experience to other people and transmit that to others, I think it forms the basis of how we get to Mars and how we explore space. Without public support, either people buying tickets to Mars or supporting NASA, I just don't think it's going to happen. So this is very much for us part of making space something that people think they can go do and do. So with that, I'll take some questions.
Great, thank you very much. First question is, so it's 8 passengers, and what's the cost that you're aiming for these flights?
So we're looking at about $125,000 a ticket. It could be more or less. We haven't set the ticket price yet. And we're also looking at a range of programs for people to fly that don't have that kind of pocket change. And actually one of the most interesting programs, we have a partnership now with Space for Humanity. We're one of their key suppliers, and they are essentially funding leadership programs to take people to the edge of space, teachers, you know, artists, etc. So by bringing the price down and providing a non-rocket experience. You're floating at 30 kilometers, but the sky is dark, the earth is curved. I think we can deliver an experience that's quite foundational to a large number of people.
Great. I was curious, you mentioned there was a pilot. So what is a pilot's responsibilities? Because it seems like, at least the thought is that balloons don't require much of a pilot. So, and you mentioned the first flight is automated. So can you speak to that?
Yeah, don't tell the pilot. So look, there are certainly contingencies and something happening with the life support system and the like that somebody on board would need to have. And there's a bit of piloting associated with bringing the balloon down to the surface of the water gracefully, but the computer does a better job than the pilot, quite frankly. It's the person on board to be the adult in the room, to stop serving the drinks, and to be there in a contingency. But it's completely flyable automatically, and it's completely flyable from the ground. And so the baseline is that essentially it's on the ground flying, and there's an automatic takeover if for some reason all communications drop out. But yes, it's a relatively straightforward piloting.
With the landing in the ocean, what's the turnaround time on reusing the capsule? Like, what do you have to do to make sure there's no corrosion from contact with the salt water?
So we're really designing it a bit like a boat. It's a boat that's also a spaceship. So by using composites and designing it for quick reuse and thinking of it like a boat in that aspect of it, it looks like we're probably a day's getting it back to port and a day refurbishing, and then a couple of contingency days. So it looks like the refurb time is something on the order of 4 days. We're then looking for the next weather opportunity to launch. So we're baselining something on the order of a flight a week per capsule, with about half of that week being the return and refurb, and half of that week being the flight. I think we can get it down to much less and do some of that refurb on the trip back, things like that. But that's what we're baselining.
And the balloon itself is reusable as well. What's the turnaround for that?
Unfortunately, the balloon is not reusable, at least not at this point. So the balloon is about 8 acres of material, and it's thin polyethylene. And so by the time it falls in the water and you get it out of the water, there's not a whole lot left of it. So we're looking at ways to make the balloon reusable and recoverable. But at this point, it's the reused part is the capsule, backup parachutes, all of that, and the balloon is not yet reusable.
Okay. And you said it goes up to 100 kilometers. Is that the height, or is there going to be any modification based on weather on how high the balloon flies?
So the standard flight is actually to 100,000 feet or 30 kilometers. So
right.
and then you can, with a balloon, we've done, you can get that mass to something like 110, 115,000 feet, but that's pretty much the limit of something on the order of 10,000 pounds.
Okay, great. And what's the total volume of the balloon? I assume it modifies as it goes up through the atmosphere?
Yes, so you start off with about 1% of the volume, and it expands 100-fold. And once it's fully inflated, it's on the order of 17 to 18 million cubic feet. So it's about 350 feet across, 400 feet across. So you could just about get a little football field inside and spin it without touching the edges. Awesome, thank you.